The universe looks endless, but it isn't. No matter how powerful our telescopes become, no matter how advanced our technology grows, there is a hard boundary that nothing can cross. A wall made of distance children's science books never mention. A limit written into the fabric of space-time itself. Today, the observable universe stretches roughly 93 billion light-years across. Not because light has travelled that far, but because space itself has been expanding the entire time the universe has existed. This means there are regions of reality that will never be reached, never contacted, never observed directly, not by humans, not by future civilizations, not even by light. In this documentary, we will explore how this invisible cosmic wall formed, why it continues to grow faster than anything can travel, and what it means for the future of exploration, physics, and reality itself. We will examine the expansion of space, the limits of observation, the cosmic horizon, and the uncomfortable truth that most of the universe is already permanently cut off from us. If you enjoy deep space documentaries that explore the boundaries of reality and the true scale of the cosmos, consider subscribing, because once you understand where this wall is, you realize how small our reachable universe truly is. The idea of a 93 billion light-year wall does not refer to a physical barrier made of matter. It refers to a limit created by time, light, and the expansion of space itself. To understand why this boundary exists, we must begin with the most important constraint in the universe. Information can only travel as fast as light. When the universe began roughly 13.8 billion years ago, it did not expand into empty space. Space itself came into existence and began expanding everywhere at once. In the earliest moments after the Big Bang, the universe was extremely hot and dense. Matter and radiation were tightly coupled. Light could not travel freely because it was constantly interacting with charged particles. Only after the universe cooled enough, about 380,000 years after the Big Bang, did atoms form and allow light to move through space without constant interruption. This moment released the oldest light we can still observe today, the cosmic microwave background. That radiation has been travelling ever since. If light has been travelling for about 13.8 billion years, it seems logical to assume that the observable universe should be about 13.8 billion light-years in radius. But this is not what we measure. Instead, the observable universe has a diameter of roughly 93 billion light-years. The reason for this discrepancy lies in how space behaves. Light travels through space, but space itself expands while light is in transit. As photons move toward us, the distance they must cross grows continuously. This stretching effect causes light to lose energy and shift toward longer wavelengths, a phenomenon known as redshift. More importantly, it increases the total distance between where the light originated and where it is observed. In other words, the light we see today from the earliest regions of the universe started much closer to us than those regions are now. Over billions of years, the expansion of space carried those regions farther away, even while their light was still travelling toward Earth. This is why the observable universe is larger than the age of the universe multiplied by the speed of light. The boundary created by this process is called the cosmic horizon. It marks the farthest distance from which light has had enough time to reach us since the beginning of the universe. Everything beyond this horizon is not visible to us. Not because it does not exist, but because its light has not yet arrived, and in many cases never will. This horizon is not static, it changes over time. As the universe ages, light from slightly more distant regions has time to reach us. In principle, this should allow us to see farther and farther. However, another effect works in the opposite direction, the accelerated expansion of space. Observations of distant supernovae in the cosmic microwave background revealed that the expansion of the universe is not slowing down, it is speeding up. This acceleration is driven by a mysterious component called dark energy, which makes up roughly 70% of the universe's total energy content. Dark energy causes space itself to expand faster over time. At very large distances, this expansion becomes so strong that it effectively outpaces the ability of light to travel toward us. This creates a second, more severe boundary known as the event horizon. The cosmic horizon tells us what we can see today. The event horizon tells us what we will ever be able to see. Beyond the event horizon, galaxies are receding from us so quickly that even light emitted now will never reach Earth, no matter how long the universe exists. Those regions are permanently disconnected from us by the expansion of space itself. This is the true wall implied by the 93 billion light-year scale. It is not a surface you could touch. It is not a structure you could approach. It is a limit created by geometry and time, and it cannot be crossed. This boundary does not violate relativity because nothing is actually moving through space faster than light. Instead, space itself is expanding. General relativity allows space to stretch at any rate. Objects embedded in that space can appear to separate faster than light without locally breaking physical laws. This distinction is subtle but essential. If a galaxy is far enough away, the expansion of space between us and that galaxy increases its distance faster than light can reduce it. Even though the galaxy is not traveling faster than light through space, the distance between us grows faster than any signal could overcome. This creates an unreachable region of the universe. From a practical standpoint, this means that cosmic exploration has a fundamental ceiling. No spacecraft, no matter how advanced, could ever reach regions beyond this horizon. Even traveling at the speed of light would not be sufficient. The universe contains more space than we can ever access. This realization changes how cosmologists think about scale. When we look deep into space, we are not only looking far away, we are looking backward in time. The farther we observe, the younger the universe appears. At the cosmic horizon, we see the universe as it was only hundreds of thousands of years after the Big Bang. But beyond that horizon lies a vast volume of space we can never observe directly. We infer its existence indirectly through models of inflation and large-scale structure, but we cannot see it. This is not a technological limitation, it is a physical one. No future telescope, no advanced civilization, no hypothetical propulsion system can overcome this constraint. The wall exists because the universe has a finite age and an expanding geometry. This leads to an unsettling implication. Most of the universe is already inaccessible. Based on current measurements, the observable universe is only a small fraction of the total universe. Inflation theory suggests that space extends far beyond what we can see, possibly infinitely. If this is correct, then the region we inhabit is a tiny island in an unimaginably larger cosmic ocean. We do not know what structures exist beyond the horizon. We do not know how matter is distributed there. We do not know whether the laws of physics remain exactly the same. These questions cannot be answered through direct observation. This does not make them unscientific. It places them beyond experimental reach. The observable universe is not the entire universe. It is simply the part that has had time to communicate with us. The 93 billion light-year boundary represents the maximum size of our cosmic information bubble. Everything inside this bubble is causally connected to us. Everything outside is not. Causality is the key concept. To influence us or be influenced by us, information must travel between regions. That requires time and a path through space-time. When expansion breaks that path, causal connection is lost. This does not mean regions beyond the horizon cease to exist. It means they exist without any possibility of interaction. From our perspective, they are forever silent. As the universe continues to expand and accelerate, this isolation will increase. More galaxies will cross the event horizon and disappear from view. Over extremely long timescales, distant galaxies will fade beyond detectability, leaving only local gravitationally bound structures visible. Future observers in distant epochs may see a much emptier universe than we do today, not because the universe became smaller, but because the observable portion shrank. This introduces a strange temporal bias. We happen to live at a time when the universe is still young enough for us to observe large-scale cosmic structure. In the far future, evidence of the Big Bang itself may become nearly impossible to detect. The wall is not just spatial, it is also temporal. It defines what can be known at different points in cosmic history. This realization forces cosmology to confront its own limits. There are aspects of reality that exist beyond empirical access, not because science failed, but because space-time itself restricts information flow. This does not undermine scientific knowledge. It defines its boundary conditions. Understanding the observable universe requires accepting that observation has a horizon. The wall at 93 billion light-years is not a mystery structure waiting to be found. It is a consequence of fundamental physics. It is the edge of our visible reality, and it is growing. As dark energy continues to accelerate expansion, more of the universe will cross beyond permanent reach. Over trillions of years, even nearby cosmic landmarks will vanish from observational possibility. This makes our era cosmologically special. We exist at a moment when the universe is still readable, when its history is still visible, when its large-scale structure can still be mapped. That window will not remain open forever. In the next part, we will explore how this wall formed during the earliest moments of cosmic inflation, why the observable universe became so large so quickly, and how tiny fluctuations in the early universe shaped the boundary we now observe. Because the wall was not created slowly, it was built in the first fractions of a second after the universe began. To understand how the 93 billion light-year boundary came into existence, we must move far deeper into the early history of the universe, into a period so extreme that ordinary intuition breaks down. This period is known as cosmic inflation, and without it, the observable universe would not look the way it does today. Inflation refers to a brief but violent phase of expansion that occurred fractions of a second after the Big Bang. During this moment, space itself expanded at an exponential rate. Regions that were once smaller than an atom grew to cosmic scales in less than a heartbeat of time. This was not ordinary expansion. It was not galaxies moving apart. It was space itself stretching faster than light could traverse it. Before inflation began, the universe was extraordinarily hot, dense, and compact. All matter, energy, and space-time were compressed into a region far smaller than anything we can directly imagine. Under these conditions, quantum fluctuations, tiny variations in energy at microscopic scales, were present everywhere. Normally, such fluctuations would remain microscopic and insignificant. Inflation changed that. As space expanded violently, these quantum fluctuations were stretched across enormous distances. What began as tiny variations became the seeds of all large-scale cosmic structure. The slight differences in density created by these fluctuations later grew into galaxies, clusters, and the vast filamentary structure of the universe. But inflation did something even more dramatic. It established the scale of the observable universe itself. During inflation, regions of space that were once in close causal contact were ripped apart faster than light could reconnect them. This means that the universe was separated into enormous domains that could no longer exchange information with each other. From that moment onward, no signal could cross the expanding gaps. This is where the foundation of the cosmic horizon was laid. After inflation ended, expansion slowed dramatically, allowing light to begin traveling across space again, but the damage had already been done. Vast regions had been pushed so far apart that they would never reconnect causally. The universe became divided into bubbles of information. We inhabit one of those bubbles. Our observable universe is not the entire universe created by inflation. It is only the region that remained close enough for light to traverse during the billions of years that followed. This means the true universe may be far larger than what we can observe, possibly infinitely larger. Inflation theory predicts that beyond our horizon, space continues in the same general structure, governed by the same physical laws, but separated from us by distances that cannot be crossed. Some models go further. They suggest that inflation may never fully stop everywhere. Instead, it may continue eternally in distant regions, constantly creating new pocket universes. In this scenario, our observable universe is one bubble among many, each potentially with slightly different physical properties. This idea is called eternal inflation. Whether or not it is correct remains uncertain, but even without invoking multiple universes, inflation alone guarantees that the observable universe is only a fraction of what exists. The size of that fraction depends on how inflation unfolded. If inflation lasted slightly longer than the minimum required to explain current observations, the universe beyond our horizon could be unimaginably vast. If inflation lasted much longer, then the total universe may be so large that our observable region is effectively negligible in comparison. This creates a strange asymmetry. We can measure the radius of what we can see with great precision, but we cannot measure the size of what lies beyond. It is not hidden behind matter or dust, it is hidden behind space-time itself. Inflation also explains why the universe appears so smooth and uniform on large scales. When astronomers measure the temperature of the cosmic microwave background, they find that it is almost identical in all directions. Regions on opposite sides of the sky, separated by tens of billions of light years, have nearly the same temperature. Without inflation, this would be impossible. Those regions would never have been close enough to exchange energy or information. Inflation solves this by placing those regions in close contact before expansion separated them. The uniformity we observe today is a fossil imprint of that early connected state, but that same process created permanent separation afterward. The early universe was unified. The modern universe is fragmented by expansion. This fragmentation defines the boundaries of observation. The cosmic horizon is not a physical edge in space. It is the edge of shared history. It marks the limit of regions that were once connected to us before inflation and subsequent expansion separated them beyond reach. Every photon we observe from the cosmic microwave background carries information from that early time. It tells us about density variations, temperature patterns, and the geometry of space-time. But beyond that shell of radiation lies silence, not emptiness. Silence. There may be galaxies, stars, planets, and structures beyond our horizon that are completely real, but permanently inaccessible. Even if the universe survives for trillions of years, no signal from those regions will ever arrive here. This has consequences for how we interpret cosmological data. When scientists build models of the universe, they rely on the assumption that what we see locally is representative of the whole. This assumption is reasonable, but it cannot be proven observationally. We cannot test whether distant regions obey the same laws of physics. We assume uniformity because inflation predicts it and because observations support it within our horizon. Beyond that, certainty ends. This limitation is not unique to cosmology. It is a fundamental property of any system governed by finite information speed and expanding geometry. But in cosmology, the scale makes it existential. The wall is not merely a technical boundary, it defines what can never be known. The realization that inflation created unreachable regions forces a redefinition of what we mean by the universe. Is the universe the totality of space-time, regardless of observability, or is it only the region we can interact with? In practical science, the observable universe is what matters. It is the only part that can be tested, measured, and confirmed. But conceptually, the true universe may be vastly larger. This creates a tension between theoretical possibility and experimental reality. Inflation theory predicts more than we can verify. Cosmology must operate within that constraint. Yet inflation is not just theoretical speculation. It is supported by precise measurements of the cosmic microwave background. The pattern of temperature fluctuations matches inflationary predictions with remarkable accuracy. The shape of those fluctuations reveals information about the geometry of space, the distribution of matter, and the behavior of early quantum fields. These measurements confirm that inflation-like behavior occurred. They also confirm that the observable universe was stretched to enormous size very quickly. Without inflation, the observable universe would be much smaller. The cosmic horizon would be closer. The structure of space would be radically different. The 93 billion light-year scale is not arbitrary. It is the result of inflation combined with 13.82 billion years of continued expansion. Together, they created a visible region far larger than intuition would suggest. But inflation also guarantees that the true universe extends far beyond that region. The wall, therefore, is not a coincidence. It is built into the origin of space-time. It is the shadow left behind by the earliest moments of cosmic history. This realization leads to an unsettling implication. There is no privileged center of the universe. Every observer, anywhere in space, sees their own observable universe with its own horizon. From any galaxy, the same kind of boundary exists. Each observer is surrounded by their own cosmic bubble. There is no global viewpoint from which the entire universe can be observed. Reality is locally accessible, but globally fragmented. This is not because of distance alone. It is because of time and expansion combined. Even if technology allowed travel near the speed of light, this would not overcome the barrier. The expansion of space itself would continue to create separation. The wall is not a destination. It is a property of space-time geometry. Understanding inflation and the horizon reshapes how we think about cosmic exploration. It shows that there is a hard limit to expansion outward, but it also reveals that the most extreme expansion already happened. Not in the future, but in the first fraction of a second after the universe began. The universe became vast almost instantly. Everything since has been refinement, cooling, and structure formation within that enormous framework. In the next part, we will examine how dark energy continues to modify this boundary today, how acceleration is reshaping the future of cosmic visibility, and why the observable universe may eventually shrink from the perspective of future civilizations. Because the wall is not static, it is moving, and the direction it is moving in determines the fate of cosmic knowledge itself. The story of the 93 billion light-year wall does not end with inflation. The universe did not simply expand rapidly and then settle into a quiet, predictable growth. Instead, a second and more subtle process began to dominate the future of space-time itself, the accelerated expansion driven by dark energy. For much of cosmic history, expansion was slowing down. After inflation ended, gravity worked to pull matter together. Galaxies formed. Clusters assembled. Large-scale structures emerged along vast filaments of dark matter. Expansion continued, but the gravitational attraction of matter acted as a brake. If this trend had continued, the cosmic horizon would slowly grow. More regions of space would gradually become visible over time as light from farther distances finally reached us. But roughly 5 billion years ago, something changed. Observations of distant supernovae revealed that the expansion of the universe was no longer decelerating. It was accelerating. This discovery was unexpected and deeply unsettling. Instead of slowing, space-time itself began expanding faster and faster. The force responsible for this acceleration was given a name: dark energy. Not because it is literally dark, but because its nature remains unknown. Dark energy does not behave like matter or radiation, does not clump. It does not form structures. It fills space uniformly and exerts a repulsive gravitational effect on large scales. The more space there is, the more dark energy there appears to be. This creates a runaway process. As the universe expands, dark energy becomes increasingly dominant. As dark energy becomes dominant, expansion accelerates further. This feedback loop has profound consequences for the cosmic horizon. While inflation created the initial separation between regions, dark energy determines how that separation evolves into the future. There are now two important cosmic boundaries. The particle horizon marks the farthest distance from which light has already reached us. This defines the observable universe today. The event horizon marks the farthest distance from which light emitted now will ever reach us. The difference between these two horizons defines the true cosmic wall. Objects currently visible may eventually cross beyond the event horizon. When that happens, they do not disappear physically. They simply become causally disconnected. Their light will never again reach us. They fade from the universe we can observe. This process is already happening. Distant galaxies are receding so rapidly that their emitted light becomes increasingly stretched and redshifted. Over time, this light weakens, fades, and eventually drops below detectability. In extreme cases, expansion causes wavelengths to stretch beyond any meaningful energy scale. Those galaxies are still there, but from our perspective, they are gone. This creates a strange asymmetry in time. In the past, the observable universe was smaller. Today, it is large. In the far future, it will appear smaller again, not because space collapses, but because accelerating expansion removes more and more regions from causal contact. In trillions of years, only the gravitationally bound local group of galaxies will remain visible. Everything else will fade beyond the horizon. Future observers may see a universe that appears empty and static, unaware of the vast cosmic structures that once filled the sky. The wall is not just a boundary in space, it is a boundary in knowledge. Dark energy makes this boundary increasingly restrictive. This acceleration also imposes an ultimate limit on exploration. Even if a civilization could travel near the speed of light, the expansion of space would prevent it from reaching distant galaxies beyond a certain distance. No amount of propulsion can overcome a metric that stretches faster than signals can propagate. This means that cosmic exploration has a shrinking target. The reachable universe is decreasing over time. This fact challenges many intuitive ideas about progress and expansion. Technology improves, but space-time geometry imposes a hard ceiling. The universe itself is pulling away faster than we can chase it. This does not mean all exploration is impossible. Local regions remain accessible. Nearby galaxies remain reachable in principle, but the dream of reaching the farthest edges of the cosmos is physically forbidden. This realization reshapes how scientists think about cosmic destiny. The fate of information becomes a central concern. When galaxies cross the event horizon, the information they carry becomes inaccessible, not destroyed, but forever separated from us by space-time expansion. This raises deep questions about entropy, thermodynamics, and the ultimate fate of cosmic structure. In a universe dominated by dark energy, matter becomes increasingly isolated. Galaxies become islands drifting apart in an ever-expanding ocean of space. Over vast timescales, stars burn out. New star formation declines as gas becomes depleted. Black holes dominate the remaining matter. Eventually, the universe enters a long, cold phase known as heat death. In this state, energy gradients flatten. Useful energy becomes scarce. The universe approaches thermodynamic equilibrium. The cosmic wall plays a role in this outcome. By isolating regions from one another, expansion prevents energy exchange across large scales. Each gravitationally bound system evolves independently towards its own fate. This isolation increases entropy on cosmic scales. It does not create chaos, it creates stillness. The wall ensures that the future universe becomes quieter, emptier, and more fragmented. But this fragmentation is not random. It follows precise mathematical rules governed by general relativity and the properties of dark energy. The speed at which space expands determines how quickly galaxies cross the horizon. This speed depends on the equation of state of dark energy, a parameter that describes how its energy density changes as the universe expands. Current measurements suggest that dark energy behaves like a cosmological constant, a fixed energy density inherent to empty space. If this is correct, acceleration will continue forever. The wall will continue to move outward relative to us, and the observable universe will gradually lose content. However, uncertainties remain. Some theories propose that dark energy could change over time. It could weaken, strengthen, or even reverse. Each possibility leads to a radically different cosmic future. If dark energy weakens, expansion may slow, allowing more regions to remain visible. If it strengthens, expansion could become extreme, eventually tearing apart galaxies, stars, and even atomic structures in a scenario known as the Big Rip. In that case, the wall would not simply isolate regions, it would destroy structure entirely. Current evidence does not support the Big Rip scenario, but it cannot be fully ruled out. What is certain is that dark energy already shapes the boundary of observability. It determines what parts of the universe will remain in causal contact over cosmic time. This makes dark energy one of the most important unknowns in physics. Understanding it is not just about explaining acceleration, it is about understanding the ultimate limits of knowledge. If dark energy remains constant, then there is a permanent event horizon. Beyond it, no information can ever reach us. This is not a technological barrier, it is a fundamental feature of space-time. The wall is built into the future. This also introduces a strange philosophical implication. The universe contains regions that will never know about us, just as we will never know about them. There is no universal cosmic conversation. Reality is fragmented into isolated domains of experience. This does not make the universe smaller, it makes it more disconnected. The wall is not a barrier between us and nothingness. It is a barrier between us and other equally real regions of space-time. From their perspective, we are beyond their horizon as well. They exist in parallel silence. This is not science fiction. It is the mathematical consequence of accelerated expansion. Dark energy did not create the horizon. It turned it into a permanent feature. Without dark energy, the horizon would slowly grow, eventually allowing more of the universe to become visible. With dark energy, that process is cut short. This makes our cosmic window temporary. We live during a brief era when the universe is still rich in observable structure. This era will not last forever. Future civilizations may inherit a sky with far fewer galaxies and far less evidence of cosmic origin. The wall will erase the visible history of the universe over time, not by destroying it, by hiding it beyond reach. In the next part, we will explore what this means for cosmic observation, how astronomers measure the horizon using redshift and background radiation, and why mapping the universe becomes more difficult as the wall advances, because the boundary is not only theoretical, it is measured. And every measurement brings us closer to understanding how much of reality is already beyond our grasp. Understanding the 93 billion light-year wall is not only a matter of theory, it is grounded in observation. Astronomers do not simply assume the existence of cosmic horizons, they measure them using light, radiation, and the large-scale structure of the universe. These measurements allow scientists to map the limits of what can be seen and to infer how much lies beyond. The most important observational tool in this process is redshift. When light travels through expanding space, its wavelength stretches. Shorter wavelengths shift toward the red end of the spectrum. The greater the expansion between the source and the observer, the stronger this redshift becomes. By measuring how much a galaxy's light has been stretched, astronomers can determine how fast it is receding and how far away it is in cosmological terms. This relationship is not simple linear motion. It reflects the expansion history of the universe itself. When scientists observe extremely distant galaxies, they are not only measuring distance, they are measuring time. Light from distant galaxies left its source billions of years ago, when the universe was much younger and smaller. By compiling redshift measurements from millions of galaxies, cosmologists build three-dimensional maps of cosmic structure. These maps reveal a vast network of filaments, voids, and clusters, a structure often described as the cosmic web. This web does not extend infinitely within observation, it fades at the horizon. Beyond a certain redshift, galaxies become too faint and too stretched to detect. Their light becomes indistinguishable from background noise. This observational limit corresponds closely to the theoretical particle horizon, but redshift alone is not enough. To precisely define the boundary of the observable universe, scientists rely on the cosmic microwave background. the oldest light we can detect. This radiation was released when the universe became transparent, roughly 380,000 years after the Big Bang. At that time, electrons and protons combined to form neutral atoms, allowing photons to travel freely. That light has been traveling ever since. Because the universe has expanded dramatically during those 13.8 billion years, the original visible and infrared radiation has been stretched into microwave wavelengths. Today, it fills the universe almost uniformly. This background radiation forms a spherical shell around us, marking the furthest distance from which any light has reached us. Every direction we look, we see the same ancient surface. This is not because it surrounds us physically. It is because we are located inside a three-dimensional light sphere created by the finite age of the universe. The cosmic microwave background defines the edge of our visible past. Beyond it lies earlier times that cannot be observed directly. By measuring the temperature and polarization of this radiation with extreme precision, scientists can infer the geometry of space, the rate of expansion, and the composition of the universe. These measurements allow the calculation of the observable universe's size. When cosmologists say the observable universe is about 93 billion light-years across, they are not estimating casually. They are using a model constrained by thousands of independent observations, supernova surveys, galaxy redshift maps, background radiation measurements, gravitational lensing, and baryon acoustic oscillations all converge on the same cosmic parameters. Together they describe a universe that is 13.8 billion years old, expanding at a specific rate and dominated by dark energy and dark matter. When these values are inserted into cosmological equations, the result is a particle horizon with a diameter of approximately 93 billion light-years. This number is not arbitrary, it is the geometric consequence of space-time expansion. But measuring the event horizon, the true wall that limits future observation, is more difficult. Unlike the particle horizon, which is based on past light reaching us, the event horizon is based on future light that will never arrive. It requires projecting the expansion history forward in time. To do this, scientists rely on models of dark energy. If dark energy remains constant, then the event horizon has a fixed radius. Beyond that radius, light emitted today will never reach Earth. This radius is smaller than the particle horizon. It defines a stricter boundary. Some galaxies we see today are already beyond the event horizon. We are receiving their ancient light, emitted billions of years ago, but any new light they emit now will never arrive. We are seeing them as ghosts from the past. This introduces a strange observational effect. We observe objects that are no longer causally connected to us. We see them frozen in time, gradually fading as their light becomes more redshifted. Eventually, even that ancient light will stretch beyond detectability. They will vanish from observation completely. This is not a sudden disappearance, it is a slow fading into invisibility. The sky is not static, it is changing on cosmic timescales. This process is measurable in principle, though far too slow to detect within a human lifetime. Over billions of years, however, the structure of the visible universe will be dramatically altered. This raises an important question. If much of the universe is already beyond our future reach, how can we be sure our cosmological models are accurate? The answer lies in internal consistency. Cosmology does not rely on a single measurement. It relies on cross-checking independent observations. The cosmic microwave background tells us about early conditions. Galaxy surveys tell us about later structure. Supernova data tells us about expansion acceleration. Gravitational lensing reveals mass distribution. When all of these agree within the same framework, confidence increases. This does not remove uncertainty. It constrains it. Within these constraints, the existence of a cosmic horizon is unavoidable. It is not an assumption, it is a prediction confirmed by observation. However, this does not mean we know everything about the wall. Its precise behavior depends on the true nature of dark energy. If dark energy is dynamic rather than constant, the horizon may evolve differently. Future observations may refine these parameters, but the existence of a boundary itself is not in question. It is embedded in the structure of space-time. One of the most powerful ways scientists visualize the horizon is through space-time diagrams. In these diagrams, time is represented as a vertical axis and space as a horizontal axis. Light travels along diagonal lines, expansion curves, space-time geometry. When these diagrams are constructed for our universe, they show clearly how some regions remain forever disconnected. There is no path light can take to cross certain boundaries. These diagrams make the wall visible mathematically. They show that the limit is not a line in space. It is a curve in space-time. This curve separates what is causally connected from what is not. Understanding this distinction is essential. The wall is not something you approach by travelling outward. It is something you encounter by moving forward in time. As time passes, the event horizon defines which regions remain connected. This also means that the wall depends on when you ask the question. What is unreachable today may have been reachable billions of years ago. What is reachable today may become unreachable in the future. The wall is dynamic. It evolves with cosmic expansion. This dynamic nature has implications for the search for extraterrestrial life and cosmic signals. If intelligent civilizations exist in distant galaxies, many of them may already be beyond our communication horizon. Even if they transmit powerful signals, those signals may never reach us. Similarly, any signals we send outward will only reach a finite region of space before being overtaken by expansion. The cosmic wall limits not only exploration, it limits communication. The universe is not only physically fragmented, it is informationally fragmented. This fragmentation grows with time. The longer the universe exists under accelerated expansion, the more isolated each region becomes. This challenges the idea of a unified cosmic civilization or universal exchange of knowledge. It may be physically impossible. The wall enforces isolation on the larger scales, yet within our observable region, extraordinary richness remains. Billions of galaxies, trillions of stars, countless planetary systems. The boundary does not diminish the complexity inside it. It only reminds us that complexity exists beyond it as well, unreachable and unseen. In the next part, we will examine what the wall means for cosmic meaning and perspective, how it reshapes humanity's place in the universe, and why the realization of unreachable space is one of the most profound insights modern cosmology has produced. Because the greatest impact of the wall is not technical, it is philosophical. It changes how we understand our position in reality itself. The discovery of a permanent cosmic boundary does more than redefine distances and expansion rates. It reshapes how humans understand their place in the universe. For most of history, the cosmos was imagined as infinite and open, a vast arena waiting to be explored. The realization that much of reality is fundamentally unreachable forces a quieter and more unsettling perspective. The universe is not only large, it is limited in what it allows us to know. This does not come from technological weakness or lack of imagination. It comes from the geometry of space-time itself. The wall does not care about curiosity, ambition, or intelligence. It is indifferent to all forms of desire. This indifference is what makes it profound. Human progress has often been driven by the assumption that boundaries exist to be crossed. Oceans were crossed, continents were mapped, the moon was reached. Even distant planets are now being studied in detail. The cosmic horizon breaks this pattern. It represents a boundary that cannot be solved by better engines or larger telescopes. It is not a challenge to overcome, it is a limit to accept. This acceptance is not defeat, it is realism on a cosmic scale. Understanding that most of the universe is inaccessible changes how scale itself is perceived. The observable universe already contains more galaxies than can be counted individually. Even within this limited region, the sheer number of stars and planetary systems stretches comprehension. Yet this enormous domain is only a small fraction of what likely exists. Reality is larger than any possible experience. This creates a strange inversion. For the first time in history, Science reveals not only how much we can know, but how much we never will. This is not ignorance in the traditional sense. It is structural ignorance. The universe is arranged in a way that makes certain information permanently unavailable. This raises deep questions about the nature of scientific knowledge. Science is built on observation and testing, but observation itself is bounded by space-time. There are truths that exist beyond the reach of measurement. This does not weaken science. It clarifies its domain. Science describes the observable universe with extraordinary precision. It does not claim authority over what lies beyond the horizon. That distinction matters. It preserves honesty. It also forces humility. Humility is not weakness. It is an accurate response to scale. The cosmic wall reveals that no civilization, no matter how advanced, can escape the limitations imposed by the universe's structure. Intelligence does not grant exemption from physical law. This insight dissolves many science fiction fantasies about intergalactic empires spanning the cosmos. Even if technological civilizations survive for millions of years, they will remain confined to finite regions of space-time. The universe is not a playground, it is a landscape with hard edges. Those edges are not physical barriers but informational ones. They define what can be interacted with. This has implications for how meaning is constructed. If the universe is largely unreachable, does that make human existence smaller or less significant? The answer depends on perspective. From one angle, the realization emphasizes insignificance. Humanity occupies a tiny region of space-time, on a small planet around an average star in a galaxy that is itself unremarkable. From another angle, it emphasizes rarity. We exist in a region of the universe that is temporarily rich in structure, energy gradients, and complex chemistry. This may be a brief window in cosmic history where life and consciousness are even possible. The wall does not diminish that rarity, it highlights it. We are not located at the center of the universe, but we are located at a special time. A time when the universe is still young enough to produce stars. A time when heavy elements exist. A time when cosmic expansion has not yet erased the visibility of distant galaxies. This temporal coincidence is remarkable. It suggests that observers like us can only arise during a narrow cosmic era. Before stars formed, there was no complexity. After stars fade, there will be little energy to sustain life. We exist in between. The wall is part of this timing. It defines not only spatial limits but historical ones. It marks the boundary of the observable past and the shrinking window of future visibility. This perspective also reframes the concept of cosmic loneliness. The possibility of life elsewhere has fascinated humanity for centuries, but even if intelligent civilizations exist beyond our horizon, they are forever unreachable. The universe may be filled with life, but it is fragmented into silent islands. No universal conversation, no cosmic network, just isolated domains evolving independently. This is not a failure of communication technology, it is a consequence of expansion. This isolation is not absolute within local regions. Nearby galaxies remain reachable for now. Signals can travel across millions of light years within gravitationally bound clusters. But on the largest scales, isolation dominates. This challenges the idea that the universe is a connected whole in any practical sense. It is mathematically connected, but causally fragmented. This fragmentation also changes how we interpret cosmic fate. In earlier models of the universe, expansion slowed and reversed. The universe could collapse back into a big crunch. In such a scenario, distant regions might eventually reconnect. Dark energy makes this unlikely. Instead, expansion accelerates. Isolation increases. The universe becomes more divided over time. This creates a future in which each region becomes its own self-contained cosmos. Local clusters evolve independently. The rest of the universe becomes invisible. In that future, observers may not even know that a cosmic horizon exists. Without visible galaxies beyond their local group, future civilizations may conclude that the universe is static and limited. The evidence of the Big Bang itself may fade beyond detectability. The cosmic microwave background will cool and stretch until it becomes indistinguishable from noise. The wall will erase history from view. This introduces a strange asymmetry. We are living at a time when the universe is still readable. We can see its origins, we can measure its expansion, we can map its structure. Future observers may not have this privilege. The cosmic wall ensures that cosmology itself is time-dependent. What can be known changes with the age of the universe. This realization adds urgency to observation, not in a dramatic sense, in a quiet one. We are observing the universe at a rare moment of accessibility. The sky we see today is richer than the sky future civilizations will inherit. This does not make our time superior. It makes it temporary access to cosmic information, temporary visibility of large-scale structure, temporary awareness of the universe's origin. This awareness does not give us control. It gives us perspective. Perspective is the real value of cosmology, not power, not dominance. Understanding the wall teaches that the universe is not designed for exploration in the way humans imagine. It is not arranged to satisfy curiosity. It simply exists according to physical law. Within that existence, life and consciousness emerge briefly. The wall reminds us that our cosmic context is constrained, but within those constraints, meaning is not reduced, it is intensified. When time and space are finite in their accessibility, experiences become more significant. Observation becomes more precious. Knowledge becomes more fragile. The fact that the universe hides most of itself does not make the visible portion trivial. It makes it rare. This also reframes ambition. Instead of dreaming about conquering the universe, the realistic ambition becomes understanding the part we inhabit as deeply as possible. Understanding matter, understanding energy, understanding life, understanding consciousness. The wall redirects focus inward rather than outward. It does not encourage isolation. It encourages depth of knowledge within finite boundaries, depth of meaning within limited reach. This is not a limitation to creativity. It is a framework for realism. Science fiction often imagines infinite expansion and cosmic civilizations spanning galaxies. Reality suggests something quieter, isolated domains of complexity separated by expanding space, evolving independently. This does not make the universe less fascinating, it makes it more strange. The strangeness is not in aliens or exotic phenomena. It is in the structure of space-time itself, a universe that creates boundaries not by walls of matter, but by stretching itself apart. A universe that hides most of its own content. A universe that allows observation only within a temporary window. The 93 billion light-year wall is not just a number. It is a statement about the nature of reality. It says that existence is larger than experience. That truth is uncomfortable, but it is also profound. In the next part, we will examine the mathematical foundations behind this boundary, how general relativity predicts horizons, and why the geometry of space-time itself produces these limits without requiring exotic assumptions. Because the wall is not an anomaly, it is the natural outcome of the equations that govern the universe. The existence of a cosmic wall is not an accident of observation. It is not a coincidence created by limited technology or incomplete measurement. It emerges directly from the mathematical structure of space-time itself. To understand why this boundary must exist, it is necessary to look at how general relativity describes the universe on the largest scales. Einstein's theory of general relativity does not treat space and time as static backgrounds. Instead, it describes space-time as a dynamic geometry shaped by energy, matter, and expansion. When this theory is applied to the universe as a whole, it leads to a specific class of solutions known as cosmological models. These models do not assume stars, planets, or galaxies at first. They assume something more basic, that on very large scales the universe is roughly uniform and isotropic. This means it looks similar in every direction and from every location when averaged over enormous distances. This assumption is supported by observation. The cosmic microwave background is nearly uniform across the sky. Large-scale galaxy surveys show similar patterns in every direction. These features allow cosmologists to use simplified equations that describe the expansion of space itself. From these equations emerges the concept of the scale factor, a quantity that describes how distances between points in space grow over time. As the scale factor increases, space expands. This expansion is not movement through space, it is the stretching of space. When the scale factor is inserted into Einstein's equations, it produces solutions that describe how light travels through expanding space-time. These solutions reveal something crucial. In an expanding universe with a finite age, there will always be a limit to how far light can travel. This is not optional, it is unavoidable. If the universe had existed forever, light from arbitrarily distant regions could eventually reach any observer. But the universe has a beginning. Time is finite. Light has only had a limited duration to propagate. This alone creates a horizon. But when expansion is included, the horizon becomes more complex. Light does not move through static space. It moves through space that stretches beneath it. This stretching increases the effective distance light must cross. In mathematical terms, this means that the path of light, called a null geodesic, is curved by the expansion of spacetime. When cosmologists integrate these light paths backward in time, they find that there is a maximum distance from which signals could have arrived. That distance defines the particle horizon. When they integrate light paths forward in time, assuming continued expansion driven by dark energy, they find that there is a maximum distance from which signals will ever arrive. That distance defines the event horizon. Both arise from the same equations. The wall is not added by hand, it emerges naturally from the geometry of space-time. This geometry is described by what is called the Friedmann-Lemaitre-Robertson-Walker metric, a mathematical representation of an expanding homogeneous universe. This metric encodes how distances evolve over time. When combined with measurements of matter density, radiation density, and dark energy, it predicts exactly how horizons form. The mathematics shows that beyond a certain distance, space-time expands so rapidly that no signal can bridge the gap. This is not because light slows down. Light always travels at the same speed locally. It is because the destination itself recedes faster than the signal can approach. This creates a one-way boundary. Signals can cross inward from nearby regions, but beyond a certain scale, outward motion dominates. The equations do not permit reversal. This is why the wall is permanent under current cosmological conditions. The geometry does not allow causal reconnection. Even if expansion slowed in the future, the separation created by dark energy would not easily undo itself. The universe would need to dramatically change its behavior to remove the horizon. This is theoretically possible in some exotic models, but current observations strongly favor continued acceleration. This makes the wall not just present, it makes it inevitable. Another important mathematical insight comes from the concept of co-moving coordinates. In cosmology, distances are often measured not in fixed units, but in coordinates that expand with space. Objects that are not moving relative to the expansion remain at fixed co-moving positions. From this perspective, galaxies are not flying away. They are stationary points embedded in expanding geometry. When cosmologists calculate horizons, they often use co-moving distances. These distances describe how much space exists between regions when expansion is factored out. The particle horizon in co-moving coordinates corresponds to the maximum region that has ever been in causal contact with us. The event horizon corresponds to the maximum region that will ever be in causal contact. These quantities are finite. This finiteness is not arbitrary. It is dictated by the integral of the scale factor over time. When that integral converges, as it does in a universe dominated by dark energy, horizons form. This convergence is a mathematical signature of permanent causal boundaries. It is not speculation, it is calculation. Another consequence of space-time geometry is the stretching of wavelengths. As light travels through expanding space, its wavelength grows with the scale factor. This redshift is not due to motion alone, it is due to geometry. This stretching means that light from distant regions becomes increasingly diluted. Energy density decreases, information becomes harder to extract. Eventually, light becomes so stretched that it is indistinguishable from background noise. This process effectively erases distant signals even before they reach the horizon. The wall is therefore not a sharp edge, it is a gradual fade, a slow loss of information as expansion weakens signals. From a mathematical perspective, this fading is inevitable in an accelerating universe. The faster space expands, the more quickly information is diluted. This introduces another important concept, the cosmic information limit. There is a maximum amount of information that can be contained within any observable region. This is related to horizon entropy, a quantity associated with the area of the event horizon. In theoretical physics, horizons are not empty boundaries. They have thermodynamic properties. They possess temperature and entropy. This idea emerged from black hole physics and extends to cosmological horizons. Just as black holes have event horizons with associated entropy, the universe itself has a cosmic event horizon with similar properties. This suggests that there is a fundamental limit to how much information can be encoded within our observable universe. The wall is not just spatial, it is informational. This connection between cosmology and thermodynamics reveals something deep. The expansion of the universe does not only shape geometry, it shapes the flow of information. As the universe accelerates, information becomes increasingly trapped within isolated regions. Entropy increases. The universe approaches a state where energy gradients flatten and structure dissolves. The wall accelerates this process by isolating systems. Isolation prevents energy exchange across large scales. Without exchange, systems evolve independently toward equilibrium. This reinforces the idea that the wall is not an arbitrary artifact, it is part of the universe's thermodynamic trajectory. The mathematical structure of space-time, the behavior of dark energy, and the laws of thermodynamics all point in the same direction, toward fragmentation, toward isolation, toward causal separation. This does not imply destruction, it implies disconnection. The universe becomes quieter, less interactive, more static on the largest scales. From a geometric standpoint, the wall is a natural outcome of expanding space with acceleration. From a thermodynamic standpoint, it is part of entropy growth. From an observational standpoint, it is the limit of what can be measured. All three perspectives converge. This convergence strengthens the conclusion that the wall is not an anomaly. It is a structural feature of reality. Understanding this also helps clarify why faster-than-light travel does not solve the problem. Even hypothetical superluminal motion would not necessarily overcome expansion. General relativity does not permit objects to locally exceed the speed of light. But even if some exotic mechanism allowed space-time manipulation, the global geometry would still impose constraints. Warping space locally does not eliminate large-scale expansion. The wall is embedded in the fabric of space-time itself. It is not a barrier you can tunnel through. It is a consequence of how the universe evolves. This realization shifts the focus from engineering solutions to fundamental understanding. The question becomes not how to cross the wall, but why the universe is structured in a way that produces it. The answer lies in initial conditions, inflation, dark energy, and the geometry of space-time. Together, these factors create a universe with built-in limits. Limits not imposed by lack of imagination, limits imposed by reality itself. In the next part, we will explore how these mathematical boundaries influence the ultimate fate of cosmic structures, how long-term expansion reshapes galaxies and clusters, and what the wall means for the far future of matter, energy, and cosmic order. Because the wall is not only about distance, it is about destiny. As the universe continues its slow drift toward isolation, the consequences extend far beyond galaxies and clusters. The cosmic wall does not simply separate regions of space. It reshapes the long-term behavior of matter, energy, and time itself. What emerges is a future defined not by dramatic destruction, but by gradual thinning, cooling, and quiet disappearance. When gravitationally bound systems become isolated islands, they evolve independently. Inside these islands, stars continue to burn for billions and trillions of years, depending on their mass. Massive stars exhaust their fuel quickly and collapse into neutron stars or black holes. Smaller red dwarf stars burn far more slowly, shining faintly but steadily for trillions of years. For an extremely long time, these dim stars will dominate the visible universe, but even they will eventually fade. When the last stars in each isolated region exhaust their nuclear fuel, no new stars will form. Gas clouds will no longer collapse. The cosmic night will deepen. This era is often called the degenerate era. During this phase, the universe is populated primarily by stellar remnants, white dwarfs, neutron stars, and black holes. These objects no longer produce significant light. They store matter in dense, compact forms. The cosmic wall plays a subtle role here. By preventing large-scale interactions, it ensures that matter remains locked inside local systems. There is no fresh inflow of gas or energy from distant regions. Each cosmic island becomes a closed ecosystem. In closed systems, entropy increases. Energy becomes less usable. Temperature differences flatten. This gradual progression toward equilibrium is unavoidable. The wall accelerates this process by isolating systems from one another. Over extremely long timescales, even stable remnants evolve. White dwarfs slowly cool, fading into black dwarfs. Neutron stars lose energy through radiation and rotational slowing. Black holes slowly evaporate through a process known as Hawking radiation. This evaporation is extraordinarily slow. A stellar mass black hole would take far longer than the current age of the universe to disappear. Supermassive black holes would persist even longer, but given enough time, timescales so large they defy ordinary language, even black holes will vanish. When this happens, the universe enters what is often called the dark era. In this era, very little structured matter remains. What exists are sparse particles, low-energy photons, and the faint afterglow of past cosmic activity. The wall ensures that this evolution occurs independently in countless isolated regions. There is no global synchronization. Each cosmic island fades on its own timeline. Some regions will retain stars longer, others will exhaust their fuel earlier. Some will host massive black holes that persist far longer than surrounding matter, but none of these regions will exchange energy or information across the horizon. The universe becomes not one continuous story, but countless disconnected ones. This fragmentation has deep implications for the concept of cosmic history. Today we can construct a unified narrative of the universe, from the Big Bang to galaxy formation to the present structure. In the far future, such a narrative becomes impossible. No observer will be able to see beyond their local region. Each observer's universe will appear small, isolated, and static. The cosmic wall erases the shared reference frame. This is not because the universe changes its laws. It is because expansion removes the ability to compare distant regions. This has implications for memory. Cosmic memory is encoded in radiation, background signals, and large-scale structure. As these signals fade beyond detectability, the evidence of cosmic origin disappears. Future civilizations, if they exist, may not be able to infer the existence of the Big Bang. They may see a quiet, nearly empty universe with no visible expansion markers. The wall hides the past as well as the distant present. This creates a strange inversion. We currently live in a time when the universe's history is visible. In the far future, the universe's origin may be unknowable, not because it never happened, but because the evidence will be beyond reach. This realization highlights the fragile nature of knowledge. Knowledge depends on accessible information. When access is removed, understanding collapses. The cosmic wall does not destroy information, it isolates it. Isolation has the same practical effect as erasure. This also reshapes how time itself is perceived. In the early universe, change was rapid, structures formed quickly, energy was abundant, interactions were frequent. In the far future, change slows dramatically. Interactions become rare, processes stretch across unimaginable durations. Time does not stop, but it becomes empty of events. This emptiness is not dramatic, it is quiet. The universe does not end with a final explosion or collapse. It fades. The wall ensures that this fading happens independently across isolated regions. There is no universal finale, only countless local endings. This decentralization of cosmic fate challenges many intuitive ideas about endings. There is no single moment when the universe ends. There is only a gradual loss of structure and interaction. The wall enforces this distributed ending. From a physical perspective, this is not tragic. It is neutral. From a human perspective, it is unsettling. Humans instinctively imagine narratives with beginnings, climaxes, and conclusions. The universe does not follow narrative structure. It follows thermodynamics and geometry. The cosmic wall is a consequence of both. It ensures that expansion and entropy work together to fragment the universe into isolated domains of fading complexity. This does not mean that complexity disappears everywhere at once. Some regions will remain active long after others fade. Some black holes will persist long after nearby stars vanish. But none of these regions will be able to influence each other. Each becomes its own quiet ending. This also reframes the meaning of cosmic scale. Scale is often imagined spatially, how far something is, how big something is. But the wall reveals that scale is also temporal and causal. What matters is not only distance, it is whether interaction is possible. Two regions separated by a few billion light years today may already be causally disconnected in the future. They exist in the same universe, but not in the same causal reality. This distinction is subtle but profound. It means that the universe is not a single interactive arena. It is a collection of domains whose connections change over time. The cosmic wall defines the boundaries of those domains. This has implications for theoretical physics. Some theories suggest that quantum entanglement and space-time geometry are deeply linked. If this is true, then cosmic horizons may not only limit classical communication, but also define deeper structural properties of space-time itself. In some models, horizons carry information encoded on their surfaces. This suggests that the wall is not empty. It is a boundary with physical meaning. Understanding this connection between horizons, entropy, and space-time remains one of the deepest open problems in physics. It links cosmology to quantum gravity. It links the largest scales to the smallest. The wall is not only about distance, it is about the structure of reality. As this understanding deepens, one conclusion becomes unavoidable. The universe is not designed for infinite expansion of knowledge or presence. It is structured around limits. Limits of speed, limits of interaction, limits of observability. These limits do not make existence meaningless. They define its shape. Within these boundaries, complexity arises, evolves, and fades. The cosmic wall is part of this cycle. It marks the edge of participation. It defines where influence ends. It shows that existence is not uniformly accessible. Reality is larger than experience. Experience is bounded. This does not reduce wonder, it intensifies it, because within a finite window of observability, an extraordinary amount of structure, beauty, and complexity exists. We inhabit that window, for now. In the next part, we will explore how these boundaries challenge human ideas of exploration and destiny, why faster-than-light concepts fail in expanding space, and how the dream of reaching the edge of the universe collides with the geometry of space-time itself, because the wall is not just a limit on observation, it is a limit on movement. The idea of reaching the edge of the universe has always carried a powerful pull. From ancient myths to modern science fiction, humanity has imagined traveling outward, crossing cosmic distances and arriving at the ultimate boundary of reality. The existence of a 93 billion light-year wall transforms this idea from fantasy into a question governed by physics. The crucial insight is that the wall is not a place. It is not a destination you can fly toward. It is a limit defined by space-time itself. In ordinary experience, travel works because space is static. When you move forward, the destination stays where it is. In the universe, on the largest scales, this assumption fails. Space is not static, it expands. And beyond a certain distance, it expands faster than any traveller can move through it. This makes the concept of reaching the edge fundamentally different from reaching a distant planet or star. Even if a spacecraft could travel arbitrarily close to the speed of light, the expansion of space would continue to increase the distance to extremely distant regions. This is not a matter of engineering, it is a property of geometry. Relativity allows objects to approach the speed of light, but it does not allow them to exceed it locally, and even approaching that limit is not enough when the destination itself is receding faster due to cosmic expansion. This means there is a maximum reachable distance. Beyond it, travel becomes meaningless. You could move forever and never arrive. The wall defines that unreachable region. This does not mean all space is unreachable. Local galaxies remain accessible in principle. The Milky Way and Andromeda will merge in the future, forming a single galaxy. Nearby clusters could be reached with sufficient time and energy, but as distance increases, expansion becomes dominant. There is a threshold beyond which movement cannot overcome space-time stretching. This threshold is not fixed, it changes over time. In the early universe, expansion was slower after inflation. Regions that are unreachable today were once reachable, but dark energy has reversed that trend. Expansion accelerates. The reachable region shrinks. This means that the window for cosmic travel is closing, not in human timescales, in cosmic ones. This realization undermines many futuristic visions. Intergalactic civilizations spanning the observable universe are physically impossible under current cosmological conditions. Even colonizing distant galaxy clusters would eventually become impossible as expansion isolates them. The universe enforces separation, not through walls of matter, through motion of space itself. This also reframes the concept of faster-than-light travel. Science fiction often imagines warp drives, wormholes, or hyperspace as ways to bypass distance. While these ideas are not strictly forbidden by all theoretical models, they face enormous physical constraints. Even if exotic space-time manipulation were possible, it would not automatically eliminate the cosmic horizon. Warping space locally does not change the global expansion of space-time. Creating shortcuts through space-time would require controlling geometry on cosmic scales. This is not merely technologically difficult, it may be fundamentally impossible. The wall is not a gap between points, it is a dynamic feature of space-time evolution. You cannot simply jump past it without rewriting the universe's expansion history. This means that the dream of crossing the cosmic boundary remains fiction, not because imagination is limited, but because reality imposes structure. The wall also challenges the idea of cosmic escape. In some narratives, civilizations flee dying galaxies or collapsing stars by traveling outward. In reality, there is no outward direction that leads to safety on cosmic scales. Every region faces the same expansion. There is no external refuge beyond the universe. The wall encloses every observer within their own causal domain. This has psychological implications. Humans often imagine the future as one of infinite expansion and outward growth. The cosmic horizon suggests the opposite. Increasing isolation. Progress may continue locally, but global expansion is not open-ended. This does not mean stagnation, it means boundaries. Within boundaries, creativity still thrives. But the fantasy of limitless outward movement is incompatible with cosmic reality. This also reshapes how exploration is valued. Exploration does not need to mean moving farther outward. It can mean understanding deeper inward. The observable universe already contains enough complexity to occupy science for millennia. Billions of galaxies, trillions of stars, unknown forms of matter and energy. The wall shifts the emphasis from expansion to comprehension. Understanding what is inside the horizon becomes more meaningful than chasing what lies beyond. This is not a defeatist view, it is a realistic one. The universe is not an infinite open field. It is a region of interaction embedded in a larger reality that cannot be reached. The wall makes this clear. Another consequence is the reinterpretation of cosmic scale. Scale is often imagined in terms of distance travelled, but the wall reveals that scale is more meaningfully measured by causal connection. 2 points separated by 1 billion light years may be more connected than 2 points separated by a smaller distance if expansion differs. What matters is not how far something is, it is whether information can travel between points. The wall defines the boundary of shared causality. This concept is more important than physical distance alone. It determines whether events can influence one another. It determines whether exploration has meaning. It determines whether communication is possible. This also affects the search for extraterrestrial intelligence. If intelligent civilizations exist beyond the horizon, they are unreachable and undetectable. They may be broadcasting signals. Those signals may never arrive. Similarly, signals sent from Earth will only reach a finite region of space. The universe is not a single communicative network, it is fragmented. This fragmentation is not temporary, it grows with time. The wall ensures that cosmic isolation increases. This does not make the universe hostile, it makes it structured. Structure is not always intuitive. It often contradicts expectations. Humans expect frontiers. The universe offers horizons. Frontiers invite crossing. Horizons define limits. This shift from frontier thinking to horizon thinking is one of the most important conceptual changes introduced by modern cosmology. It moves humanity from expansion fantasies to acceptance of cosmic boundaries. This acceptance does not eliminate ambition. It redirects it. Instead of reaching outward endlessly, ambition turns inward toward understanding physical law, mastering local environments, and exploring the depths of matter and energy. The wall does not limit curiosity, it limits reach. Curiosity can still extend infinitely. Knowledge does not require physical travel across cosmic distances. It requires insight. The cosmic horizon forces a distinction between physical expansion and intellectual expansion. Physical expansion is finite, intellectual expansion is not. This distinction is important. It preserves the future of exploration as a mental and scientific endeavor. Even when physical exploration is bounded, the wall also introduces a new kind of cosmic humility. Humans are not central, not spatially, not temporally. We exist in a region of space-time that happens to be accessible to us. We are not privileged observers of the whole, we are localized participants. This does not reduce significance, it contextualizes it. Significance comes not from size but from awareness. The universe may be mostly unreachable, but the part we inhabit is enough to generate meaning, complexity, and understanding. The wall is not a denial of wonder, it is a reframing of it. Wonder is not located beyond the horizon. It is already present within it. In the next part, we will explore how cosmologists visualize and model these boundaries, how simulations reveal the structure of expanding space, and how future observations may refine our understanding of the wall's behavior. Because while the wall is a limit, our understanding of it continues to expand. To understand the cosmic wall more clearly, scientists do not rely on imagination alone. They build mathematical models, massive simulations, and observational reconstructions that allow the structure of space-time to be visualized in ways the human mind cannot naturally grasp. These tools do not remove the boundary, they reveal how deeply it is embedded in the architecture of the universe. Modern cosmology operates on scales so vast that direct experimentation is impossible. Instead, researchers reconstruct cosmic history by combining physical laws with observational data. The result is not a single picture, but a family of models that describe how the universe evolves over billions of years. One of the most powerful tools is large-scale cosmological simulation. In these simulations, supercomputers model billions of particles representing dark matter, gas, radiation, and cosmic expansion. The equations of gravity and space-time expansion are applied step by step, allowing structure to form naturally over time. When these simulations are run forward, something remarkable happens. The cosmic web emerges. Filaments stretch across enormous distances. Voids form between clusters. Galaxies gather along dense intersections. The structure observed in real astronomical surveys appears spontaneously in the simulated universe. But these simulations also reveal something else. They show how expansion stretches these structures apart. When dark energy is included, the simulated universe gradually fragments. Large-scale connections weaken. Distant clusters drift beyond interaction range. Over time, isolated islands of matter remain. This matches theoretical predictions of the event horizon. The simulations show that the cosmic wall is not just a mathematical abstraction, it shapes the future distribution of matter. Another important visualization comes from space-time diagrams. These diagrams do not show space alone, they show space and time together. Light paths appear as diagonal lines. Expanding space curves the geometry. Horizons appear as boundaries that no signal can cross. In these diagrams, the cosmic wall is not drawn as a vertical line, it is a curve. This curve marks the limit of causal influence. Everything inside the curve can exchange information with the observer. Everything outside cannot. These diagrams make it clear that the wall is not a place you travel to, it is a property of time evolution. You do not encounter the horizon by moving outward, you encounter it by waiting. As time passes, regions drift beyond reach. The horizon is crossed by galaxies, not by observers. This distinction is subtle but important. It means the wall moves relative to us even if we remain stationary. The universe is actively removing regions from our causal domain. Another key observational technique involves measuring baryon acoustic oscillations. These are faint patterns in the distribution of galaxies that originate from sound waves in the early universe. They act as a cosmic ruler. By measuring how these patterns appear at different distances, scientists can reconstruct the expansion history of the universe. This expansion history directly determines the size and behavior of the cosmic horizon. Supernova measurements provide another independent method. Type Ia supernovae act as standard candles. Their brightness allows astronomers to measure distances across billions of light years. These measurements revealed the acceleration of expansion and confirmed the presence of dark energy. Without dark energy, the cosmic wall would behave differently. With it, the horizon becomes permanent. Cosmic microwave background measurements provide the deepest view. They allow scientists to reconstruct the universe when it was only 380,000 years old. The tiny temperature fluctuations in this radiation encode information about density, geometry, and expansion. When this data is combined with galaxy surveys and supernova observations, a consistent picture emerges. The universe is expanding, the expansion is accelerating, horizons exist, and they impose real limits. This convergence of independent evidence is what gives scientists confidence. The wall is not speculation. It is a prediction tested by observation. However, uncertainty remains in the details. Dark energy is still poorly understood. Its exact nature is unknown. It could be a cosmological constant, a fixed energy of empty space. It could be a dynamic field that evolves over time. It could be a sign that gravity behaves differently on the largest scales. Each possibility changes the precise behavior of the horizon, but none eliminate it entirely. All realistic models produce some form of causal boundary. This means the wall is robust against theoretical variation. Its existence does not depend on fine-tuned assumptions. It emerges from the basic structure of space-time expansion. Another area of active research involves quantum cosmology. Some theories suggest that space-time itself emerges from deeper quantum processes. In these models, horizons may be connected to entanglement and information flow at a fundamental level. This suggests that the cosmic wall may not just be a classical geometric boundary, it may be tied to the deepest structure of reality. If space-time is built from quantum information, then horizons define where that information can flow. This creates a connection between cosmology and quantum gravity. The largest scales and the smallest scales intersect at the horizon. Understanding this connection remains one of the greatest challenges in physics. It requires unifying general relativity with quantum mechanics. The cosmic wall sits at the center of this problem. It is where classical geometry meets quantum information limits. This makes it more than a distant boundary. It is a testing ground for fundamental theory. Another surprising consequence of horizon physics is the idea that the universe may contain more information on its boundaries than in its volume. This idea comes from holographic principles inspired by black hole physics. In these models, the maximum amount of information in a region is proportional to the area of its boundary, not its volume. If this applies to cosmological horizons, it implies that the cosmic wall encodes information about everything inside it. This is not fully understood, but it suggests that horizons are not empty. They are active participants in the structure of reality. From this perspective, the wall is not just a limit, it is a feature with physical content. This deepens its significance. It transforms it from a passive boundary into an active part of cosmic dynamics. Another aspect revealed by simulations is the asymmetry of cosmic time. The universe evolves from a hot, dense, highly interactive state to a cold, sparse, isolated one. This arrow of time is reinforced by the cosmic wall. As expansion isolates regions, the ability to reverse large-scale processes disappears. The universe becomes increasingly irreversible. This irreversibility is not imposed externally, it emerges naturally from expansion and entropy growth. The wall accelerates this irreversibility by cutting off interaction. It ensures that large-scale coordination becomes impossible. This is why the far future universe is predicted to be quiet and static, not because nothing exists, but because nothing interacts. Interaction is what creates visible change. Without it, the universe becomes observationally empty. This emptiness is deceptive. It hides complexity behind horizons. It hides matter behind expansion. It hides history behind redshift. The wall creates an illusion of simplicity, but beyond it lies unreachable structure. This illusion has consequences for future observers. They may misinterpret the universe. They may conclude that it is static, empty, and eternal. They may never know about cosmic inflation, the Big Bang, or large-scale structure. The wall erases context. This makes current cosmological knowledge fragile. We are dependent on our position in cosmic time. If we existed billions of years earlier or later, our view of the universe would be radically different. This temporal dependency is another effect of the horizon. The wall is not just a spatial boundary, it is a filter applied by time. It determines what era of the universe can be observed. This filter will shift. What we can see today will not always be visible. This makes our current era uniquely informative. It is a moment when the universe is still transparent enough to reveal its origin and structure. That window will not remain open forever. This realization gives cosmology a sense of urgency. Not urgency in the human sense of speed, but urgency in the cosmic sense of opportunity. We have access to information that future observers may never see. The wall will hide it. In the next part, we will explore what this means for humanity's long-term relationship with the universe, how knowledge preservation becomes important in a fading cosmos, and why the greatest challenge may not be crossing the wall, but remembering what existed before it closed. As the cosmic wall continues to advance across space-time, it creates a new challenge that extends beyond physics and astronomy. It introduces a problem of memory, not memory in the human sense of individual experience, but memory in the cosmic sense, the preservation of knowledge about the universe's origin, structure, and evolution in a future where the evidence itself will slowly vanish. Today, the sky is filled with information. Galaxies trace the expansion of space. Background radiation carries the imprint of the early universe. Gravitational waves echo ancient cosmic events. Together, these signals allow humanity to reconstruct a detailed story of cosmic history, but the wall ensures that this situation is temporary. As expansion accelerates, distant galaxies will fade beyond detectability. The cosmic microwave background will cool and stretch to wavelengths too long to measure. Even gravitational wave backgrounds will become diluted beyond recognition. Future observers may inherit a universe that appears quiet, empty, and static. Without visible expansion markers, they may conclude that the universe has always been this way. The story of the Big Bang could become unknowable, not because it is false, but because the evidence will be inaccessible. This introduces a strange responsibility for present observers. We exist at a time when cosmic history is still readable. We can measure the age of the universe, we can infer inflation, we can observe the large-scale structure. These capabilities may not exist forever. This makes the current era unique. It is a window of cosmic clarity. That clarity will close. The wall does not just limit travel, it limits memory. This has implications for how knowledge is valued. Scientific knowledge is often treated as permanent once discovered, but in a universe with expanding horizons, even well-established truths may become unverifiable in the future. Future civilizations may rediscover physics locally. They may study stars, atoms, and chemistry, but without access to cosmic-scale evidence, their understanding of cosmology may be incomplete or fundamentally different. They may not know the universe began in a hot, dense state. They may not know about inflation or dark energy. They may not know that galaxies once filled the sky. The wall does not erase reality, it erases access to contexts. This possibility forces a rethinking of scientific legacy. What does it mean to preserve knowledge across cosmic timescales? Human civilizations typically think in terms of centuries or millennia. Cosmology operates on billions of years. The gap is enormous. Any attempt to preserve cosmic knowledge must contend with timescales far beyond the durability of current technologies or institutions. Data storage media degrade, civilizations rise and fall, languages change, even planets may not remain stable environments. Preserving information across cosmic eras is not simply a technical challenge, it is a fundamental problem of entropy. Entropy does not only apply to energy, it applies to information. Without active maintenance, information decays. The wall accelerates this decay by removing external references. In a universe with fewer observable features, independent verification becomes harder. Knowledge becomes more fragile. This creates a paradox. At the moment when the universe is most observable, civilizations capable of understanding it are just emerging. At the moment when civilizations might be most advanced, the universe may become observationally barren. There is no guarantee that these timelines align. This raises deep questions about the relationship between intelligence and cosmic evolution. Is it coincidence that intelligent observers appear during a brief window of cosmic transparency? Some scientists argue that this is not coincidence. They suggest that complex life requires specific conditions that only exist during certain cosmic eras. Heavy elements must be present, stable stars must exist, energy gradients must be available. These conditions do not exist in the early universe. They may not exist in the far future. Life emerges in the middle. The wall is part of this middle phase. It defines the end of cosmic openness. This makes our era cosmologically rare. not because humans are special, but because the universe itself passes through phases. We happen to exist during one of the most information-rich phases. This does not grant privilege. It creates responsibility, not moral responsibility, scientific responsibility. If cosmic knowledge is temporary, then documenting it becomes meaningful beyond immediate utility. This perspective shifts science from mere discovery to preservation. Not preservation of objects, preservation of understanding. This is not a sentimental idea. It is a realistic response to a universe that forgets. The universe does not remember its own past. It leaves traces. Those traces fade. If no one records them, they disappear from accessible reality. This introduces a new dimension to cosmology. Cosmology is not only about what exists, it is about what will be remembered. The cosmic wall will erase large-scale evidence. The only remaining record may be internal, stored in artificial archives, encoded in durable media, or embedded in long-lived structures. But even these are vulnerable. No storage system is immune to entropy. Over trillions of years, even the most robust constructions will degrade. This suggests that cosmic memory has a natural lifespan. Eventually, the universe becomes observationally amnesiac. This does not mean reality disappears. It means knowledge of reality fades. The difference is important. The wall does not destroy matter, it destroys access. This distinction mirrors a broader truth. Existence does not guarantee awareness. Awareness depends on interaction. When interaction ends, awareness fades. The cosmic wall enforces this separation on the largest scale. This also reframes the meaning of discovery. When scientists discover something about the universe, they are not uncovering an eternal truth in a static environment. They are capturing information during a fleeting window of accessibility. The wall makes discovery time-sensitive, not in the sense of urgency, in the sense of opportunity. There is an opportunity to understand the universe while it is still visible. That opportunity will not last forever. This perspective changes how cosmology is framed. It becomes less about conquering knowledge and more about documenting a transient state of reality. Reality is not static, it evolves. Our access to it evolves as well. The wall is one of the forces driving that evolution. It ensures that the universe becomes progressively more difficult to observe. This has consequences for the future of science itself. Future civilizations may develop advanced technology but lack cosmic data. They may have powerful particle accelerators and quantum computers, but without observable galaxies or background radiation, they may not be able to reconstruct cosmological history. Their physics may be deeply local. They may know everything about atoms and stars, but little about the origin of the universe. This inversion is striking. Technological sophistication does not guarantee cosmological understanding. Understanding depends on cosmic visibility. The wall controls visibility. This also challenges the assumption that scientific progress is linear and cumulative. In a universe with fading evidence, progress may plateau or even reverse in certain domains. Knowledge can be lost not because of ignorance, but because of missing data. This is not a failure of intelligence. It is a consequence of cosmic structure. The wall introduces irreversibility into knowledge. Once certain signals fade beyond detection, they cannot be recovered. There is no way to reconstruct information that never arrives. This irreversibility mirrors the thermodynamic arrow of time. Entropy increases. Information becomes less accessible. Order gives way to uniformity. The cosmic wall accelerates this process by isolating regions. This creates a future where the universe becomes simpler in appearance even as its underlying complexity remains. The appearance of simplicity is misleading. It hides unreachable complexity beyond horizons. This hidden complexity does not benefit observers. It might as well not exist from their perspective. This raises philosophical questions about the nature of reality. Is something real if it can never be observed or interacted with? Physics answers yes. Experience answers no. The cosmic wall separates physical reality from experiential reality. It defines two layers of existence, one that exists, one that can be known. This distinction is uncomfortable, but it is fundamental. The universe is larger than knowledge, always has been. The wall makes that explicit. In the next part, we will explore the final implication of this boundary, what it means for the ultimate fate of cosmic meaning, how humans relate to a universe that hides most of itself, and why the wall transforms cosmology from a story of expansion into a story of limits. Because the greatest impact of the wall is not physical, it is existential. As the consequences of the cosmic wall move beyond observation and memory, they begin to touch something deeper. The way intelligent beings interpret their existence inside a universe that is fundamentally larger than what can ever be experienced. The wall does not simply impose physical limits, it reshapes the psychological and philosophical relationship between observers and reality itself. For most of human history, the unknown was assumed to be temporary. What could not be seen today might be seen tomorrow. What could not be reached now might be reached later. Progress was imagined as a steady expansion of access. The cosmic horizon breaks this assumption. It introduces permanent unknowns, not mysteries waiting to be solved, but regions that will never enter any observer's causal sphere. They are the result of geometry. This forces a new understanding of ignorance. There is ignorance caused by lack of knowledge, and there is ignorance enforced by space-time. The second kind cannot be eliminated. It can only be acknowledged. Many technological civilizations measure progress by how much territory they can explore and how many resources they can access. The universe itself sets a boundary on that expansion. No matter how advanced a civilization becomes, it remains confined to a finite causal region. This confinement is not political, it is cosmological. It applies equally to every possible observer anywhere in space. There is no escape from the horizon. This realization reframes ambition. Ambition no longer points outward without limit. It becomes inward-facing. It focuses on depth rather than distance. Instead of conquering space, the realistic goal becomes understanding the structure of reality within the accessible domain. Instead of spreading across the universe, civilizations adapt to living inside bounded cosmic bubbles. This does not make ambition smaller, it makes it more precise. The universe is not infinite in what it allows, it is infinite in what it contains. That difference matters. The wall also reshapes the concept of uniqueness. When people imagine the vastness of space, it is easy to feel insignificant. But the presence of a cosmic horizon creates a different perspective. Each observable region becomes a unique universe in practice. Not in theory, but in experience. Every observer occupies the center of their own cosmic bubble. From their perspective, they are surrounded by a horizon beyond which nothing can be observed or influenced. This does not make them special in absolute terms, but it makes their local universe complete in experiential terms. Each bubble contains its own history, structure, and future. There is no global vantage point from which all bubbles can be compared. Reality is fragmented into isolated observational domains. This fragmentation does not destroy unity at the level of physical law. The same fundamental principles apply everywhere, but it does break experiential unity. No observer can experience the whole. This forces a shift in how meaning is constructed. Meaning can no longer be derived from totality. It must be derived from locality, from what is accessible, from what can be interacted with. This is not a limitation unique to cosmology. It reflects a broader truth about existence. All experience is local. The cosmic wall simply magnifies this truth to the largest possible scale. Another psychological implication of the wall is the redefinition of cosmic loneliness. Loneliness is often imagined as the absence of others. In a universe with horizons, loneliness takes on a new dimension. It is not just that civilizations may be rare, it is that even if they are common, many are unreachable. There may be countless intelligent beings beyond our horizon, but they might as well not exist from our perspective. The wall creates existential isolation, not emotional isolation, causal isolation. This isolation does not require emptiness. It exists even in a universe filled with life. The inability to interact creates the same effect as absence. This challenges the idea that connection is guaranteed by existence. Existence does not imply contact. Contact depends on space-time structure. The cosmic wall defines the limits of connection. This realization is unsettling. It removes the comforting idea that the universe is one connected community of matter and life. Instead, it reveals a mosaic of disconnected regions, each evolving independently. There is no universal stage, only local theatres. This perspective also affects how time is experienced. Time is often thought of as a universal flow that applies equally everywhere. In practice, time is experienced locally. The cosmic wall enforces this locality. Different regions experience different cosmic histories. Some regions will lose visible galaxies earlier, some will retain star formation longer, some will become observationally empty sooner than others. There is no synchronized cosmic clock. There is no universal now across the entire universe. The wall enforces temporal fragmentation. This fragmentation makes the universe less like a single story and more like countless parallel stories that never intersect. Each story unfolds within its own causal bubble. This changes how cosmology is interpreted. Cosmology is often presented as the story of the universe. In reality, it is the story of one observable region. There may be many such stories unfolding beyond reach. They may be similar, they may be different. We cannot know. This uncertainty is not ignorance in the usual sense. It is structural unknowability. Accepting this requires a shift in how certainty is valued. Certainty becomes local. Global certainty becomes impossible. This does not undermine science. It clarifies its scope. Science does not describe everything that exists. It describes everything that can be observed and tested. The cosmic wall defines the boundary of that domain. This boundary also forces a re-evaluation of existential meaning. If most of reality is unreachable, does that make our existence insignificant? Or does it make the accessible portion more meaningful? There is no single answer, but one interpretation stands out. Meaning does not come from size. It comes from interaction. The fact that we can observe, measure, understand and reflect on the universe within our horizon is remarkable. The wall does not remove wonder, it concentrates it. Wonder becomes focused on what is available rather than what is unreachable. The observable universe is already vast beyond comprehension. It contains more galaxies than grains of sand on Earth's beaches. It contains more stars than any civilization could ever count. It contains physical processes that stretch the limits of theory. The wall does not make this smaller. It places it in context. Context is not reduction, it is framing. The wall frames the observable universe as a finite domain of interaction, embedded in a larger, unknowable reality. This framing changes how humans relate to cosmic scale. Instead of being overwhelmed by infinite distance, attention shifts to finite accessibility. This shift can be stabilizing. Infinity is abstract and ungraspable. Finite horizons are concrete. They define a space in which understanding can operate. Another implication of the wall is the reinterpretation of destiny. Many narratives imagine a final cosmic outcome that applies to everything, everywhere. The wall suggests that destiny is local. Different regions will experience different endings. Some will lose stars earlier, some will retain black holes longer, some will reach thermal equilibrium sooner. There is no single cosmic finale, only distributed conclusions. This decentralization of destiny mirrors the decentralization of observation. There is no central ending, there is no universal climax. The universe does not converge toward a single dramatic event. It disperses. The wall enforces this dispersion. This challenges human storytelling instincts. Stories usually have beginnings and endings. The universe has a beginning, but it does not have a unified ending. It fades differently in different places. This fading is not dramatic, it is quiet. The wall contributes to this quietness by isolating regions and reducing interaction. This quiet future is not necessarily bleak, it is neutral. It is the natural outcome of expansion and entropy. The emotional reaction to it depends on perspective. Some may see it as emptiness, others may see it as calm. The universe does not assign value to its own evolution. Value is created by observers. Within the horizon, observers can still find meaning, purpose, and complexity. The wall does not eliminate those possibilities, it limits their scope. Another subtle implication is the redefinition of exploration. Exploration is often imagined spatially, moving outward into unknown territory. The cosmic horizon suggests a different kind of exploration. Exploration of laws, exploration of structure, exploration of time, exploration of information. Instead of traveling across unreachable distances, exploration becomes an inward process, understanding the deepest mechanisms that govern the accessible universe. This inward exploration may prove far richer than outward travel ever could. Understanding dark energy, quantum gravity, and space-time geometry may reveal more about reality than traveling to distant galaxies. The wall redirects curiosity from motion to comprehension. This redirection is not a limitation, it is a transformation. The universe invites understanding, not conquest. It offers structure, not infinite territory. This perspective aligns more closely with reality. The cosmic wall teaches that the universe is not built for unlimited expansion of influence. It is built for localized complexity within global isolation. This is not a design, it is a consequence, but it shapes everything that follows. In the next part, we will bring these ideas together and examine the ultimate meaning of the 93 billion light-year boundary. Not as a number, not as a distance, but as a fundamental feature of existence that defines what it means to live inside an expanding universe. Because the wall is not just a boundary in space, it is a boundary in understanding. When all of these threads are brought together, the 93 billion light-year wall stops being just a scientific measurement and becomes something far more fundamental. It becomes a structural feature of reality, a rule that shapes what can be known, what can be reached, and how existence unfolds across time. At its core, the wall exists because the universe is not static. It expands, it evolves, it carries space itself outward. This expansion does not simply rearrange galaxies, it reorganizes causality. Causality determines what can influence what. It defines which events can affect others and which remain forever separate. The cosmic wall is the boundary of this influence. It is the line between shared history and permanent separation. This has a profound implication. The universe is not one continuous stage where everything interacts with everything else. It is a collection of regions whose connections are constantly changing. Some regions remain in contact, others drift into isolation. The wall is the mechanism that enforces this separation. This realization reframes the idea of cosmic unity. Physically, the universe may be governed by universal laws, but experientially it is fragmented. No observer can ever witness the whole, no civilization can ever interact with all of reality. There is no universal viewpoint, every perspective is local. This is not a limitation of intelligence, it is a feature of space-time. Understanding this shifts how knowledge itself is defined. Knowledge is not simply about discovering objective facts, it is about accessing information within a bounded domain. Outside that domain, facts may exist, but they remain inaccessible. This distinction matters. It means that reality is larger than knowledge by design, not by accident. The universe is structured in such a way that some truths remain forever beyond observation. This is uncomfortable for human intuition, which often assumes that enough effort can solve any problem. The cosmic wall contradicts this assumption. There are questions that cannot be answered, not because they are poorly framed, but because the universe does not allow the necessary information to reach us. This does not make inquiry pointless, it gives it context. It clarifies where investigation is meaningful and where speculation begins. The wall also changes how cosmological humility is understood. Humility here does not mean lowering expectations or abandoning curiosity. It means recognizing the difference between what can be explored and what must remain theoretical. It means accepting that the universe does not owe observers complete access, it simply exists according to physical law. Within that law, horizons form. Those horizons are not failures, they are consequences. Another important implication of the wall is the separation between existence and experience. Something can exist beyond the horizon and still be real in every physical sense, but if it can never be observed, influenced, or interacted with, it becomes irrelevant to experience. This does not make it imaginary, it makes it causally disconnected. This separation introduces two layers of reality. There is the total universe, everything that exists, and there is the observable universe, everything that can never be known directly. The wall is the boundary between these two layers. This boundary is not fixed. It changes with time, but it never disappears. This layered reality challenges many assumptions about objectivity. Objectivity is often defined as describing reality independent of perspective, but when access itself is limited, perspective becomes unavoidable. Every observation is local. Every measurement is bounded. There is no way to step outside space-time and see the whole. This does not mean that scientific laws are subjective. It means that scientific access is constrained. The laws may apply universally, but observation does not. This distinction becomes important when interpreting cosmological models. When scientists talk about the size of the universe beyond the observable region, they rely on extrapolation. These extrapolations are grounded in theory and supported by local evidence, but they cannot be directly confirmed. The wall enforces this uncertainty. It ensures that some aspects of reality remain inferential rather than observational. This does not invalidate cosmology. It defines its scope. It reminds us that models describe what is most likely, not what is directly verified beyond the horizon. This nuance is often lost in popular discussions of the universe. The wall restores it. Another deep implication concerns the relationship between time and distance. In everyday experience, distance is spatial and time is separate. In cosmology, they are intertwined. The farther we look, the further back in time we see. The wall is not just the edge of space. It is the edge of observable history. Beyond it lies a region whose past light has not reached us and may never reach us. This means there are events that have already happened beyond our horizon that we will never know about. Supernovae have exploded, galaxies have merged, stars have been born and died. All of this has occurred in regions that will never communicate with us. History exists without witnesses. This challenges the idea that observation defines reality. Reality unfolds regardless of observers. Observation only captures a slice. The wall defines the thickness of that slice. This also introduces a new way of thinking about cosmic time. Time is not just a sequence of moments, it is a filter. It determines which events become observable and which remain hidden. As the universe ages, this filter changes. Some events become visible, others fade away. The wall ensures that the visible record of the universe is incomplete and temporary. This impermanence of cosmic records has consequences for how the future will interpret the past. Future civilizations may not have access to early cosmic signals. They may reconstruct physics using local experiments, but the grand narrative of cosmic evolution may be lost. This loss is not due to ignorance, it is due to expansion. The universe itself erases its own traces, not violently, gradually. This slow erasure is one of the most subtle effects of the cosmic wall. It does not announce itself. It quietly removes information from view. Another implication is the separation of fate. In a universe without horizons, Distant regions could eventually influence each other. Matter could mix. Energy could redistribute globally. With horizons, this is impossible. Each region evolves independently. This independence leads to divergent cosmic futures. Some regions may retain star formation longer. Some may become dominated by black holes earlier. Some may experience rare catastrophic events. There is no single cosmic future. There are many parallel futures unfolding in isolation. The wall enforces this multiplicity. This also means that no universal cosmic equilibrium exists. Thermodynamic equilibrium is approached locally, not globally. The universe does not settle into one uniform final state. It fragments into isolated equilibria. This fragmentation contradicts many intuitive models of cosmic endings. There is no final universal temperature. There is no final uniform distribution. There are only disconnected outcomes. This decentralized ending reflects the decentralized nature of cosmic expansion. The wall is the mechanism that prevents reunification. Understanding this changes how cosmic destiny is framed. Destiny is not singular, it is plural. Each region has its own fate. This perspective reduces the idea of a grand cosmic narrative. There is no single story that includes everything. There are countless overlapping stories that never meet. This is not chaotic, it is structured. It follows physical law. The cosmic wall enforces this structure. It defines the boundaries of interaction. Another consequence is the redefinition of scale in terms of relevance. Beyond the horizon, scale becomes meaningless in practical terms. Whether the universe beyond is finite or infinite, structured or chaotic, filled with galaxies or empty voids, none of it affects what happens inside our causal region. This does not make it irrelevant in theory, it makes it irrelevant in practice. The wall forces cosmology to separate physical existence from experiential relevance. This separation clarifies priorities. Understanding the accessible universe becomes more important than speculating endlessly about unreachable regions. Speculation can inspire, but it cannot be tested. The wall draws a line between science and metaphysics, not sharply, but clearly. Science operates inside the horizon. Beyond it lies inference and theory without verification. This boundary is not arbitrary. It is enforced by space-time. Accepting this boundary does not diminish the value of cosmology. It deepens it. It adds realism. It prevents false certainty. It encourages careful distinction between what is known, what is inferred, and what is unknowable. This intellectual honesty is one of the most important outcomes of understanding the cosmic wall. The wall does not only limit, it clarifies. It clarifies the structure of reality. It clarifies the limits of observation. It clarifies the scope of science. It clarifies the nature of existence in an expanding universe. In the final part, we will bring all of these insights together and reflect on what the 93 billion light-year wall ultimately represents, not just as a physical boundary, but as a defining feature of the universe that shapes how life, knowledge, and meaning emerge within finite cosmic horizons. Because the wall is not simply something far away, it is something that quietly defines everything we can ever know. When the full weight of the 93 billion light-year wall is finally understood, it becomes clear that this boundary is not just an astronomical measurement or a technical detail of cosmology. It is one of the most fundamental features of existence itself. It defines the relationship between reality and awareness, between what exists and what can be experienced, between infinity and limitation. The universe may be vast beyond comprehension. It may extend far beyond what any telescope will ever see. It may contain structures, events, and histories that will never intersect with ours. Yet all of that immensity is filtered through a simple constraint. Information can only travel so far, and space itself is constantly stretching that distance. This creates a universe that is larger than perception, not metaphorically, literally. There is more reality than experience can ever contain. This realization reshapes the meaning of scale. When people speak of the size of the universe, they often imagine distance alone. But scale is not only about kilometers or light years, it is about accessibility. It is about interaction. It is about causal connection. The wall is the boundary of relevance, not in a philosophical sense, in a physical one. Everything beyond the horizon exists without consequence for anything inside it. No signal from those regions will ever arrive. No action taken there will ever affect what happens here. The separation is absolute. This does not make the unreachable universe meaningless. It makes it disconnected. Meaning arises through interaction. Without interaction, there is no shared context. The wall enforces this separation on the largest possible scale. This leads to a strange inversion of perspective. The observable universe, which already feels impossibly large, becomes a small island of interaction inside a far greater ocean of unreachable space. Yet within that island, all of human history, all scientific discovery, all cultural meaning, and all conscious experience unfolds. Everything that will ever matter to observers like us happens inside this finite region. The wall does not make existence smaller, it concentrates it. It focuses all experience into a bounded domain. This concentration has implications for how purpose is interpreted. If most of the universe is unreachable, then purpose cannot be defined by cosmic conquest or expansion. It cannot be defined by occupying space. It must be defined by what happens within the horizon. This does not trivialize human activity. It reframes it. Meaning is not derived from controlling the universe. It is derived from understanding and engaging with the part of reality that can be accessed. The wall quietly redirects ambition from domination to comprehension. It suggests that the highest form of exploration is not outward expansion, but deeper understanding. Understanding the laws of physics, understanding the structure of space-time, understanding the emergence of complexity and consciousness. These pursuits do not require crossing the horizon. They require insight. This also changes how progress is measured. Progress is often imagined as increasing reach, more territory, more expansion, more influence. The cosmic wall shows that reach has a hard limit. Influence cannot extend indefinitely. Progress, therefore, becomes less about spatial growth and more about informational depth. The universe allows infinite questions within finite boundaries. This is not a constraint on curiosity, it is a framework for it. Another implication is the reinterpretation of cosmic insignificance. Humans often feel insignificant when confronted with the scale of the universe. The wall introduces a different perspective. Yes, the universe is vast, but it is also fragmented. Each observable region is its own complete experiential universe. There is no central observer. There is no privileged location. Every observer occupies the center of their own horizon. From this perspective, significance is not about being large, it is about being aware. Awareness is rare in the universe as far as we can tell. It arises only under specific conditions. Those conditions exist within certain cosmic windows. We exist within one of those windows. The wall makes this clear by showing that existence and experience do not scale together. The universe can be enormous without being experientially infinite. This distinction is subtle but important. It means that feeling insignificant because of size alone misses the point. What matters is not how much exists, but how much can be experienced. The observable universe already exceeds any capacity for full comprehension. Within that region lies more complexity than any civilization could exhaust. The wall does not reduce wonder, it defines its boundaries. Another deep implication is the relationship between freedom and constraint. At first glance, the cosmic wall seems to restrict freedom. It limits movement, it limits communication. It limits exploration, but freedom is always defined within constraints. No system is free without boundaries. Biological systems function within physical limits. Societies function within resource limits. Minds function within cognitive limits. The universe functions within space-time limits. The wall is one of those limits. It does not eliminate freedom, it shapes it. Freedom becomes the freedom to explore within reachable space, to understand within observable reality, and to create meaning within finite horizons. This type of freedom is not infinite, but it is real. Infinite freedom is abstract. Finite freedom is actionable. The wall transforms cosmic freedom from a fantasy into a grounded reality. Another implication concerns the nature of destiny. Without a cosmic wall, it might be possible to imagine a future where the universe becomes unified again, where distant regions reconnect, where global coordination occurs. The wall eliminates this possibility. It ensures that the universe evolves toward fragmentation rather than unification. Destiny becomes decentralized. Each region evolves independently. There is no global future. There are countless local futures unfolding in isolation. This decentralization of destiny mirrors the decentralization of observation. There is no single narrative that applies everywhere. There is no universal ending. There is no final cosmic event that gathers everything together. The universe does not culminate, it disperses. This dispersion is not chaotic. It is structured by expansion and entropy. The wall enforces it. Understanding this removes many anthropocentric assumptions about cosmic importance. The universe does not revolve around observers. Observers emerge briefly within it. They observe part of it, then they fade. The universe continues. The wall ensures that this continuation happens without global coordination or reunion. This perspective can feel unsettling. It removes the idea of cosmic purpose imposed from outside, but it also removes the burden of cosmic expectation. The universe does not demand meaning. Meaning is created locally, within the horizon, within experience. This is where human significance resides. Not in controlling the cosmos, but in interpreting it. Another consequence of the wall is the recognition that limits are not flaws, they are features. They give structure to existence. Without limits, nothing would be defined. Without horizons, there would be no distinction between what is reachable and what is not. Boundaries create shape. The cosmic wall gives shape to reality on the largest scale. It defines the arena in which physics, life, and consciousness operate. This arena is finite in reach, but vast in content. That balance is what makes complexity possible. Infinite uniformity would not produce structure. Finite horizons allow gradients, differences, and interactions. The wall is part of this structural balance. It prevents total homogenization. It preserves localized complexity. This is not obvious at first glance, but without horizons, the universe could evolve toward uniformity more quickly. By isolating regions, the wall allows independent evolution. This independence produces diversity. Different regions follow different paths. This diversity is invisible to us beyond the horizon, but it exists. The universe becomes a patchwork of isolated complexity. This patchwork nature of reality is rarely discussed, but it is a natural consequence of expansion. The wall enforces it. Understanding this also changes how humans relate to the idea of cosmic endings. Instead of imagining a single dramatic finale, the wall suggests a quieter outcome. There is no universal collapse. No final explosion, no ultimate convergence. There is gradual isolation, gradual fading, gradual quiet. This ending is not cinematic. It is subtle. It is slow. It is governed by thermodynamics rather than spectacle. This subtlety reflects the true nature of cosmic evolution. The universe does not follow narrative arcs. It follows physical laws. The wall is one of the outcomes of those laws. It is not an exception. It is a rule. Perhaps the most important realization is this: the cosmic wall does not make the universe smaller. It makes our relationship to it clearer. It shows that reality is not defined by what we can reach, but by what we can understand. It shows that existence is larger than experience, but experience is still meaningful. It shows that boundaries do not eliminate wonder. They frame it. Within the horizon lies enough mystery, beauty, and complexity to occupy civilizations for as long as they exist. Beyond it lies silence, not emptiness. Silence imposed by space-time itself. The 93 billion light-year wall is not something waiting to be crossed. It is something quietly shaping every observation, every measurement, and every interpretation of the cosmos. It defines the edge of our visible reality, and in doing so it defines what it means to exist inside an expanding universe. Not infinite, not central, but aware, within a finite window of cosmic possibility. As the understanding of the cosmic wall deepens, one final transformation occurs. The realization that this boundary does not merely limit observation or movement, it reshapes how reality itself is structured from the inside. The universe does not behave like a single continuous arena. It behaves like a collection of causally separated regions, each carrying its own version of cosmic history, each evolving in isolation, each bound by the same physical laws but unable to exchange information. This creates a universe that is unified in principle, yet fragmented in practice. The laws of physics operate everywhere in the same way. Gravity bends space-time, light follows geodesics. Energy is conserved locally, expansion stretches space uniformly. But the effects of these laws are experienced differently in each cosmic bubble defined by a horizon. From inside any given region, the universe appears centered around the observer. The horizon surrounds them in all directions. This is not because the observer is special. It is because horizons are observer-dependent. Every observer carries their own cosmic boundary. Wherever you are in the universe, you will always see yourself at the center of your observable region, not physically at the center of all space, but causally at the center of what can be known. This destroys the idea of a single cosmic perspective. There is no view from nowhere. Every view is anchored to a location in space-time. The cosmic wall makes this explicit. It forces cosmology to accept that perspective is unavoidable. This has profound implications for objectivity. Objectivity does not mean removing perspective entirely. That is impossible. It means understanding the limitations of perspective and correcting for them where possible. Cosmology achieves this by using physical law to extrapolate beyond observation. But extrapolation is not the same as direct access. The wall ensures that there will always be a boundary between what is measured and what is inferred. This boundary does not weaken science. It strengthens it by preventing false certainty. Another implication is the changing nature of cosmic identity. When humans imagine themselves as part of the universe, they often imagine belonging to a vast, interconnected whole. The cosmic horizon introduces a more nuanced picture. We belong to a region, not to the totality. Our cosmic identity is local. This does not isolate us emotionally. It contextualizes us physically. We are part of a causal neighborhood. Everything that can ever affect us lies within that neighborhood. Everything beyond it is physically irrelevant to our future. This local identity is not a limitation, it is a definition. It tells us where influence ends. It tells us where responsibility applies. It tells us where action has meaning. This becomes especially important when considering long-term survival and planning. Civilizations often imagine expanding outward indefinitely, colonizing distant galaxies, building networks across the cosmos. The cosmic wall sets a hard boundary on these ambitions. There is a maximum reachable region. Within that region, planning makes sense. Beyond it, no strategy applies. This forces a shift from expansionist thinking to sustainability thinking. Instead of asking how far civilization can spread, the more meaningful question becomes how long it can endure within finite boundaries. Longevity becomes more important than reach. Stability becomes more important than scale. The wall redirects future-oriented thinking from growth to persistence. This shift mirrors trends already present on planetary scales. Infinite growth is impossible in finite environments. The universe itself enforces the same principle on the largest scale. Bounded systems require balance. The cosmic horizon makes the universe a bounded system from the perspective of any observer. This also affects how energy resources are understood. Energy cannot be imported from beyond the horizon. No future technology can harvest power from unreachable regions. All usable energy must come from within the causal bubble. This places absolute limits on long-term energy budgets. Stars will eventually burn out. Black holes will slowly evaporate. The universe will cool. The wall ensures that no external energy source can replenish these losses. This makes energy management a fundamental cosmic constraint, not just an engineering problem. It is written into space-time geometry. This also reshapes how scarcity is interpreted. Scarcity is not only a result of resource depletion, it is a consequence of isolation. Even if energy exists elsewhere in the universe, it is inaccessible. For practical purposes, it does not exist. The wall transforms abundance into scarcity through separation. This effect is subtle but unavoidable. It applies equally to matter, energy, and information. Information beyond the horizon might exist, but it cannot be used. Matter beyond the horizon might exist, but it cannot be accessed. Energy beyond the horizon might exist, but it cannot be harvested. The wall defines what is physically relevant. Another implication is the reinterpretation of cosmic risk. Some threats originate locally: supernovae, asteroid impacts, gamma-ray bursts. Others might originate from distant regions. The cosmic wall limits which threats can affect us. Events beyond the horizon cannot harm us. They also cannot help us. The universe becomes divided into zones of relevance and irrelevance. This creates a natural shield, not a protective barrier, but a causal one. The horizon protects by isolating. This is not intentional. It is structural. This has interesting consequences for cosmic safety. As the universe expands and horizons tighten, the number of potential external threats decreases. Isolation reduces risk, but it also reduces opportunity. Everything becomes local. Another subtle effect of the wall is its influence on the perception of motion. In everyday life, motion is defined relative to objects. In cosmology, motion is defined relative to expanding space. Galaxies beyond a certain distance are not moving through space faster than light. Space itself is expanding between us. This distinction is critical. It means that nothing is violating relativity. The wall emerges naturally from allowed physics. Understanding this prevents misconceptions about faster-than-light motion. No object locally exceeds the speed of light. The apparent superluminal recession is a property of space-time expansion. This reinforces the idea that the wall is not exotic. It is ordinary relativity applied on cosmic scales. Another consequence concerns the concept of borders. In human societies, borders are artificial. They are drawn by agreements and conflicts. The cosmic wall is not artificial. It is not drawn. It emerges. It is not negotiated. It is enforced by physical law. This makes it fundamentally different from any boundary humans have created. It is not political. It is not cultural. It is not historical. It is structural. This makes it one of the few absolute boundaries in nature. Another important implication is the relationship between presence and absence. The wall creates regions of absence not because nothing exists there, but because nothing can be observed there. Absence becomes observational rather than physical. This changes how emptiness is interpreted. The universe may appear emptier in the future not because matter disappears, but because it becomes unreachable. Appearance and reality diverge. This divergence is one of the most profound effects of the horizon. What is seen does not equal what exists. This has implications for interpretation. Future observers may draw incorrect conclusions about cosmic content. They may underestimate the amount of matter and energy that exists beyond their horizon. They may believe the universe is smaller than it truly is. They may believe they occupy a unique position. The wall creates illusions of centrality and simplicity. These illusions are not deliberate, they are unavoidable. Understanding this helps avoid anthropocentric bias. It reminds us that our current view is temporary and limited. Another implication is the emotional response to cosmic boundaries. Some may feel constrained. Others may feel relieved. Limits can feel restrictive, but they can also provide structure and stability. Knowing the boundaries of what is possible allows meaningful planning. It removes false hope and false fear. The wall provides clarity. It defines the playing field of cosmic existence. Within that field, complexity unfolds. Beyond it lies unreachable reality. This clarity is not depressing, it is grounding. It situates humanity inside a real universe with real limits. Not an infinite abstraction, a structured physical system. This realism is important for mature cosmological thinking. It moves discussion away from fantasy and toward physical truth. Another consequence is the relationship between scale and relevance. Just because something is large does not mean it matters to local evolution. The unreachable universe may be enormous, but it does not influence what happens inside the horizon. Relevance is defined by causality, not size. This is counterintuitive. Humans tend to associate importance with magnitude. The wall shows that importance is defined by interaction. Small local events can have enormous consequences. Distant cosmic structures beyond the horizon have none. This inversion reshapes intuition. It makes local processes more significant than distant abstractions. This perspective aligns with physical reality. The universe operates locally. Global properties emerge from local interactions. The wall enforces this locality on the largest scale. As we approach the final understanding of the cosmic wall, one idea becomes unavoidable. The universe is not built for unlimited access. It is built for structured limitation. Within those limits, extraordinary complexity arises. Life emerges. Consciousness forms. Civilizations appear. Science develops. Meaning is created. All of this happens inside finite horizons. The wall does not prevent this. It enables it by providing stable causal domains. Without horizons, large-scale uniformity might dominate. Boundaries allow differentiation. Differentiation allows structure. Structure allows complexity. In this sense, the cosmic wall is not an enemy of existence. It is one of its conditions. In the final part, we will bring this understanding to its conclusion and reflect on what the 93 billion light-year boundary ultimately teaches about the nature of the universe, not as a distant wall in space, but as a defining principle that shapes reality, limits access, and frames the stage on which all observable existence unfolds. Because the wall is not just something we observe, it is something we live inside. The 93 billion light-year wall is not simply the farthest distance we can see. It is not just a number attached to the observable universe. It is a quiet rule that shapes everything about how reality unfolds, how knowledge forms, and how existence is experienced inside an expanding cosmos. When this boundary is fully understood, it becomes clear that the universe is not built for total access. It is built around horizons, horizons of light, horizons of influence, horizons of memory. These horizons are not flaws in the universe, they are structural features of space-time itself. They arise naturally from the expansion of space and the finite speed at which information can travel. Together, these two simple facts create a reality where most of existence is permanently beyond reach. This does not make the universe incomplete, it makes it layered. There is the layer of total existence, everything that physically exists across space-time, and there is the layer of observable reality, everything that can ever be experienced by any observer. The cosmic wall separates these layers. This separation defines the limits of knowledge. No technology, no civilization, no intelligence can cross this boundary through effort alone. It is not a challenge to be overcome, it is a condition to be understood. The universe does not invite conquest, it invites comprehension. Within the horizon there is more than enough complexity to occupy minds for as long as minds exist. The observable universe contains billions of galaxies, trillions of stars. and physical laws that continue to reveal deeper layers of structure. Even within a finite domain, reality is vast beyond practical exhaustion. The wall does not reduce wonder, it focuses it. It forces attention onto what is accessible rather than what is unreachable. This shift is subtle but powerful. It changes the orientation of curiosity. Instead of pointing outward endlessly, curiosity turns inward, toward understanding spacetime, matter, energy, and the emergence of complexity within finite boundaries. This is not a retreat. It is an alignment with reality. The cosmic wall also teaches that existence does not require infinity to be meaningful. Meaning does not arise from unlimited space. It arises from interaction, awareness, and the ability to reflect on experience. All of this happens inside horizons. Everything that has ever been thought, created, discovered, or imagined exists within causal boundaries. Human history unfolds entirely inside a tiny fraction of the observable universe, and yet within that fraction entire civilizations rise and fall, knowledge accumulates, art is created, science advances, and consciousness reflects on its own origin. Scale alone does not determine significance. Connection does. The wall reveals that connection is always local. Another lesson of the cosmic horizon is the impermanence of cosmic knowledge. We live during a rare era when the universe is still transparent enough to reveal its origin. The cosmic microwave background, distant galaxies, and large-scale structure are still observable. This window will not remain open forever. As expansion continues, evidence will fade beyond detection. Future observers may inherit a universe that appears smaller, emptier, and more static than it truly is. This does not make current knowledge fragile, it makes it precious. We exist at a moment when the universe is still readable. This does not grant special importance to humanity, it reflects the timing of cosmic evolution. Intelligent observers emerge during a period when stars are abundant and information is accessible. The wall marks the beginning of the closing of that period. This perspective transforms cosmology into more than a scientific pursuit. It becomes a form of preservation of cosmic history, preservation of understanding, preservation of context, not for eternity, because eternity is not available, but for as long as memory can be maintained. The wall also reframes the concept of cosmic endings. There is no single final moment when the universe stops. There is no universal collapse or ultimate explosion. Instead, the universe slowly fragments into isolated regions that evolve independently. Each region experiences its own fading of structure. Each loses access to the rest. Each becomes quieter over time. The wall ensures that the universe does not end in unity. It ends in separation. This is not tragic. It is neutral. It is the natural consequence of expansion and entropy. The emotional interpretation of this outcome depends on perspective. Some may see it as loss, others may see it as calm. The universe itself does not assign meaning to its own evolution. Meaning is created locally, within the horizon, within experience. Another important realization is that boundaries do not eliminate freedom, they define it. Freedom without limits is abstract and unusable. Freedom within structure is actionable. The cosmic wall defines the arena in which physical freedom operates. It tells us what is possible and what is not. It removes illusions of infinite expansion and replaces them with realistic possibilities. Within those possibilities, creativity still thrives. Civilizations can still explore their local universe. They can still develop technology. They can still understand physical law. They can still search for meaning. None of this requires crossing the horizon. It requires curiosity and persistence. The wall does not block intellectual exploration. It only blocks physical reach. This distinction is crucial. It preserves the future of science even as physical expansion becomes limited. Another subtle lesson of the wall is humility. Not the humility of weakness, the humility of realism. It reminds us that the universe is not designed around observers. Observers arise within it. They are subject to its structure. The universe does not adapt to human desire. Human understanding adapts to the universe. This is the foundation of mature science. It accepts reality as it is, not as it is wished to be. The cosmic horizon is a reminder that nature sets the rules. Not ambition, not imagination, not hope. Understanding those rules is more powerful than attempting to escape them. The wall also teaches that presence is more important than reach. Being fully aware of the accessible universe is more meaningful than dreaming endlessly about unreachable regions. Presence allows engagement. Reach without interaction is meaningless. The universe offers presence within horizons. It does not offer total access. This balance is not arbitrary. It is a consequence of space-time geometry. Finally, the 93 billion light-year wall reveals something deeply counterintuitive. The universe is unimaginably large, and yet every observer lives inside a finite cosmic bubble. Within that bubble, all of their reality unfolds. Everything they will ever know, everything they will ever experience, everything that will ever matter to them. This does not make the universe small. It makes experience finite. And within that finitude, meaning becomes possible. The cosmic wall is not an obstacle placed in front of humanity. It is the edge of the stage on which all observable existence takes place. It defines the boundaries of cosmic experience. It shapes the flow of information. It determines the limits of influence. It frames the relationship between reality and awareness. We will never cross it, not because we lack technology, not because we lack intelligence, but because the universe is structured around horizons, and within those horizons, life emerges. Questions are asked, understanding grows, and consciousness reflects on the strange fact that it exists at all. The wall does not end curiosity. It gives it a shape, a finite shape, a meaningful shape. And inside that shape, the universe becomes not something to conquer, but something to understand.